Okay, good morning. Uh, let's start. So you can start video recording as well. Okay, can you see the screen?
Yes, sir.
Okay, good. So let's start where we left off. We stopped at this result that the set 0, 1, the open interval on the real line, right, between 0 and 1 is uncountable. And as I said, this was proved by Cantor in the mid 19th century. And he gave a novel proof based on a technique called diagonalization, which we'll be using later on in the course. It is a very widely used technique in computability and complexity theory. Okay. So the proof is by contradiction. So assume that you can enumerate all the real numbers between 0 and 1 in this sequence, say R0, R1, R2, and so on, right? And we are going to use the fact that every real number between 0 and 1 can be expressed. So every x in this set can be expressed as an infinite decimal expansion. Okay. So all these numbers are of this form. They can be expressed in this form. You have the digit following the decimal point, you have the digit D0, then D1, D2, and so on. And this is an infinite sequence, right? For instance, 1/3 is, well, I'll drop the 0. It's just an infinite sequence of 3's after the decimal point. There is a technical point here. If you want to express 3/10, this actually has two representations. One is 0.30 and a sequence of zeros. But this can also be expressed as this continuing decimal. Okay? So this number 3/10 has two representations. And this causes some technical problems. So we'll just say that we will not use this one and use this one. So we won't have a trailing sequence of zeros in any number. Instead, we'll have numbers like these, right? This is just a technical point, right? So once we do that, because we have an enumeration, so for every natural number, there is a real number in that 0, 1 interval. So let's say the real number corresponding to 0 is the decimal point followed by D00, D01, D02, and so on. And similarly, right? So this will be D10, D11, D12, so on, D20, D21, D22, and so on. And similarly, you can write down the, this is something I'll have to get better at. For the nth, for the row n, you will have dn0, dn1, dn2, and so on. And by the way, this holds for all real numbers in this interval, 0, 1, whether they're rational or irrational. Okay? Because every irrational number can also be expressed as an infinite decimal expansion. Okay? So we use that fact, right? Now, by assumption, this is a 1-to-1 correspondence. Then what we do is we look at this diagonal right? We look at the this number R, which is given by this diagonal. So it's this infinite decimal expansion D00, D11, D22, and so on, DNN, right? And then we tweak this. So this number is also between 0 and 1. And we tweak this number slightly so that every digit is changed, right? So for instance, we can add 1 to each of these digits, right? So 0 will become 1, 1 will become 2, and so on. And for 9, we change it to 0. Okay. This is just one way of doing it. There are many other ways. So we obtain another number say R dash, which is which has all the digits different from the one here, from R, right? So all these digits are different from the one above. Then we can claim that this R dash will not appear anywhere in this table, right? Why is that? Can somebody answer that?
So because there's at least one digit that differs.
Yes, that's true. So for argument's sake, suppose you say that R dash appears in the ith row, right? But then by the construction of the table, the ith element in the ith row is not the point. It's DII, that's the digit here, right? But by construction, R dash, the ith digit after the decimal point is different from DII. That's by constraint. So what we have is a number which does not appear in the enumeration, which is of course a contradiction, which says that this mapping is not onto, right? So this technique is known as diagonalization. And this is a very important technique. And we'll come back to it later in the course when we talk about computability. And this was first used by Cantor, as I said. Okay. So that is our overview of, we are coming to the close of our overview of cardinality, but you can use the same technique to show, and you should do it yourself, that the set of infinite sequences over the Booleans 0 and 1 is uncountable. It's essentially the same technique. You should show that. Number two, if you take the set of finite sequences, over 0, 1, is this countable or uncountable? Anyone?
So countable.
Countable.
It is count. Can you give a brief reason why that is the case?
The Cartesian product of a finite set tends to be countable.
No, but this is, sorry, this is not, you are saying if I take all strings of length, I mean, all sequences of length n, that's a n-fold Cartesian product. So that would be true. I mean, your argument would be true for that, but I'm talking about all finite sequences, right? Of arbitrary length. So how you can give an enumeration, right?
So
What
we
is
could
the
just
enumeration?
convert it to its decimal form, that we could consider it as a Boolean number.
Decimal form.
I mean, base 10.
But there's, you know, zeros and all. So there's a bit of because trailing zeros, if two numbers have different number of trailing zeros, so it's, you don't have to do all that. All you got to do is to enumerate them.
So
And
you can
yes,
you can arrange them lexicographically.
that's right. So you can start with sequences of length 0, and there is only one sequence of length 0. Then enumerate sequences of length 1. Okay, so there are just two, 0 and 1, and then sequences of length 2, 0, 0, and you can do it lexicographically. Okay, so you can do that, and you should also be able to show that for any set S, there is no bijection between S and the power set of S, which we write this way, right? And remember, S can be infinite. So just saying that if S has n elements, then the power set of S has 2 to the power. That works only for finite sets. I'm talking about any set here. Huh? You must keep this in mind. In this, we don't talk about just finite sets, right? So this also you can show using diagonalization, and I leave it to you, right? I mean, these are really from discrete maths. So if you don't know how to do it, you should refresh your knowledge. But let me just come back and say that from all this, what can we conclude about the number of programs in a programming language. Or the set of programs in a programming language. Is it countable or is it uncountable?
So I think it's countable because it's like a set of finite sequences over.
Yeah, because of two.
Yeah, because of two.
Because you can think of the every program being a sequence of ASCII characters. Okay. So because the ASCII set is finite, right? So the set of finite sequences over any finite set, not just the binary set, is countable, right? So that tells us that the number of programs we have is countable. On the other hand, if you take the set of all functions, okay, from a countable set to say the set of all functions from the natural numbers to just the booleans. So this is nothing but this is isomorphic to the power set of the natural numbers. And of course, that is uncountable. So the set of all such functions is uncountable. On the other hand, the number of programs is countable. So this immediately tells us that there are functions for which there are no programs, right? In other words, there are functions which cannot be computed by any program, okay? And I'm just talking about functions which evaluate to either 0 or 1. But you can take the natural numbers to natural numbers as well, because this set is even bigger, right? So this is all uncountable. So this immediately tells us that there are functions which are not computable by any program, okay? All right, so this is our review of cardinality. If you have any questions, please ask me now. Because I'm going to start something, the main content of the course right away. So if you have any questions, you can ask me. Anything so far? Any doubts? By the way, I have uploaded the first lecture in Teams. There's a section called class material. So I've uploaded the first lecture, right? And the video has already been uploaded, but I thought the quality of the video was not so good. But anyway, I think you can manage. So any comments? If there aren't any comments, then let's start our study of formal languages. And the most basic concepts here are alphabets and strings. And strings are often called words. I think this book uses strings what if you look at books and papers from Europe, they prefer words. Okay, so what is an alphabet? Alphabet is just a finite non-empty set. Okay, and we usually denote it by this Greek letter sigma. This is the capital Greek letter. So it is both finite and non-empty. That's important. For instance, we have the binary alphabet, which we just saw. Right? And we have the usual alphabet of Roman letters. Okay, the elements of the set sigma are called symbols or letters sometimes. So this is lowercase, right? Anyway, so that's an alphabet. So essentially a finite set of symbols, right? Then we define what is a string or a word. Right? So this is nothing but a finite sequence of symbols of sigma. And usually we denote these strings by the letters U, V, W, and so on. And examples are 0, 1, 0, 0, 1, 1. So that's a string. Or A, B, C, D, A. So that's a string. And we also have the empty string, the empty sequence. And the way to denote it is by using the small Greek letter epsilon, right? But some books also use lambda. We'll use epsilon in this course. So that's a string. It's just a finite sequence, right? We want to talk about infinite sequences of symbols in this course, but that's also an important notion. An infinite string or infinite word. So there's a whole theory behind that, but we won't study that in this course. Okay. If some of you are interested in formal verification and model checking, I mean, infinite words and automata on infinite words, they play a major role there. Okay. But that's only taught in an elective course. And it is usually taught by me. And most of you will probably never encounter those things in your life. That's okay. But these finite sequences are important. Okay. So because every sequence has a length, we define the length of a string, say W. So this is just the set of the number of symbols or the number of positions. Number of positions. in the string, right? So the empty string epsilon has length 0, right? And A, B, C has length 3, right? Okay. Next, we define an operation on strings that's called concatenation. So if U is a string, if U and V are strings, then the concatenation of U and V is written U dot V, or sometimes we just drop the dot and just write UV, just as we do in multiplication. So what is this new string? Well, it's the string U followed by the string V, right? So you append the sequence V at the end of U, right? So that's concatenation, right? And right, so the next important thing is we can define the set. If sigma is an alphabet, then sigma star is defined to be the set of all finite strings over the alphabet sigma, okay? And notice that this is an infinite set. For example, if sigma is the binary alphabet, then sigma star has the empty string, all strings of length 1, strings of length 2, and so on. So this is an infinite set. It is a countable set, as we just saw. It's a countably infinite set, right? So that's the definition of sigma star. And we can also define sigma plus. This is the set of all finite non-empty strings over sigma. That is, it is sigma star set difference. You just take away the element empty string. So if you drop the empty string from this set, what you get is sigma plus, which is the set of all finite non-empty strings. Sigma. Okay. So any questions so far? Any doubts? Okay. The next important definition is that of a language. over an alphabet sigma, right? So you are given an alphabet sigma, which, as we defined, is just a non-empty finite subset of symbols. What is the symbol written after this one? Set difference. Okay, some people write it as sigma star minus the singleton. So this notation is also used. So this is set difference. So which symbol are you talking about? Oh, this one. This is just a definition. Some people write something like this. Yeah, okay. So what is a language over an alphabet, language L over an alphabet sigma, right? This is just a subset of sigma star. Okay. That is, a language is a set of strings over the alphabet sigma. Okay. Example. Suppose sigma is the binary alphabet. So sorry, let me drop this from here. Right? So this is a language, and this is this is the language of all strings, which have a number of ones, a finite number of ones, followed by a zero and ending with a zero. Right? Okay, so that's L1. Set of all strings sigma, or sorry, I use W. Right? This is different from L2 is different from L1 because it says nothing about the initial part of the string. All it says is it ends with a 0. So this is actually the set of all the binary representation of all even numbers. Okay. Similarly, W is a palindrome, right? So all of you know what a palindrome is, right? So a word that looks the same when it is reversed. So this also includes the empty string, right? That's a palindrome. 0 and 1 are palindromes. And 0, 0, 0, 1, sorry, 1, 1. Palindromes, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1. Any other palindromes of length 3? These are the only ones, right? Yeah, and so these are all examples of languages. So a language is a set of strings, right? And a language can be either infinite or finite. The examples I've taken are all infinite languages, but they can be finite. It can be a finite set also. Number 4, the set of all strings that contain an equal number of zeros and ones. So that's also a language. That's also infinite. Okay. Yes. Any questions? Okay, just as we defined concatenation of strings, we can define concatenation of languages. Right? So if L1 and L2 are languages, then L1, L2, I'm just dropping that dot, is the set of all strings UV, that is U concatenated with V, such that U belongs to L1 and V belongs to L2. Is this definition clear? Right. In other words, a string in L1, L2, the concatenation of L1 and L2 is a string in L1 followed by a string in L2. Then you can also define powers of languages. So L to the power n is just the n-fold concatenation of L. And inductively, it can be defined as follows. L to the power 0, and this is for any natural number n. So L to the power 0, any idea? What it should be?
Epsilon.
Well, it's the singleton set containing epsilon, right? Remember, this is a language, right? Epsilon is a string, and this is a language, right? And then Ln plus 1 is just L to the power n followed by L. Here's an example. Suppose L, let me take a finite language here. Suppose it is epsilon 0, 1, 1, 0, right? So what is L to the power 0? It is just epsilon. The singleton set containing epsilon. L to the power 1 is just L, because when you concatenate epsilon with any word, you get that word, right? So epsilon is the unit of concatenation. In fact, I don't know whether you've studied an algebraic structure called a monoid. You may have studied groups in some vast course. This set, sigma star, the set of all strings with concatenation and epsilon, is a monoid, meaning that this concatenation operation is associative, and this epsilon is the unit. Okay, so that's just as an aside. So L to the power 1 is L, and what is L squared? Well, if you concatenate epsilon with epsilon, you get epsilon. If you concatenate epsilon with any other string here, you get that same string, right? And then you have to concatenate 0, 1 with all the strings. So 0, 1 concatenated with epsilon is 0, 1, right? Then 0, 1, 0, 1, and 0, 1, 1, 0, and then 1, 1, 0 is already there. 1, 0, 0, 1, and 1, 0, 1, 0. So did I miss out anything? Yeah? Did I miss out anything here? I think it's okay. And similarly, you can do all that, right? Once you know what concatenation of languages is, you can do this. Right? So any questions so far?
Sir, does language necessarily contain the empty sequence?
No, not necessary.
Okay, sir.
And I've given some examples. In fact, L1, L2, L1 and L2 are examples of languages which don't contain epsilon, right? Whereas L3 and L4 are languages which contain epsilon, right? Okay. So far, so good. How much time do we have? Okay, we have about 10 minutes. So we can define. So we have defined languages, and now we are going to define a kind of a machine, which is called a deterministic finite automata. So this is a very restricted kind of machine. And let me just give a formal definition here, and we'll take up examples in the next class. So this machine, this will just refer from now on, we'll just call it a DFA, deterministic finite. So this machine has several components, right? And let me write them down. So there are 5 components. So this is a 5 tuple. Right? Where Q is a finite set of states. So Q is a set of states, and that is finite. Okay? And it's important that the set of states is finite. So you can think of the states as being the memory of the machine. And sigma, as earlier, is a finite alphabet. So it's a finite set of symbols. And delta is a state transition function. Okay. So it takes a state and a symbol, an input symbol, and gives you a new state. Right? So that's called the transition function. This Q naught is just an initial state. So it's an element of capital Q. And finally, capital F is a set of final, also called accepting states. So this is a deterministic finite automata. There's a set of states. There's a finite alphabet, which is often called the input alphabet. Right? There's a transition function. And There is an initial state, right? And there's a set of final states. So these are the components of a machine. And it's important to see that this delta is a function which means, first of all, that it's a total function. When we say function, we mean a total function. So for every q and every sigma, there must be a delta. I mean, for every state, small q, and every letter, symbol A, there must be a state delta QA. That's what I mean. Okay, because this is a function. And there is exactly, so given a state and a symbol, there is exactly one new state. Okay. So what is the behavior of this machine? Well, this machine you can think of as, let me draw a picture, right? Suppose your sigma input alphabet is AB, right? Then this is small w, so given an input word, a string. So this is a string over this alphabet. What the machine does is, here's the machine, M. It starts reading the input word from the very first symbol, the input string. And initially, it is in the initial state Q now, right? And when it reads an input letter, it transitions to a new state. And the new state is given by this transition function, delta, right? So initially, the state is Q0, right? Once it reads this input letter, so after reading the first symbol, which is A in this case, the new state is delta Q0, comma A. Okay? And the machine will move to will scan the next symbol. So this is how it behaves, right? So it reads this you can think of as the input tape, which is divided into cells, and the machine just scans the input symbols on the tape from left to right, and it starts in the state Q0, and whenever it reads a symbol, it moves to a new state given by the transition function, and it scans the next symbol, right? And by the time it comes to the end of the tape, if it is in a final state, then we say that the input string is accepted by the machine. Otherwise, we say it is rejected. So at any stage, the machine would be reading some symbol in the string. It would be reading some symbol in the string, and it will be in some state Q. So in one step, it will transition to a new state and move one cell to the right. Okay. And it'll keep on moving right till it reads the last symbol. And after reading the last symbol, if it transitions into a final state, that is a state in capital F, then it accepts that input string, otherwise it rejects the string. Okay, so this is the behavior. So let me stop because I've already exceeded my time. Okay, so if there are any questions, I'll take it up in the next class, which is next week. Okay. Okay. Okay, bye then.